Hi guys, this is Mr. Adams from Midway High School, and this is a video on topic of organic chemistry. As always, please be safe, okay, and follow all the guidelines. Alrighty. Now, this topic right here of organic chemistry, right, is very important, and you will need your reference tables, everyone. Okay, so please find your reference tables. We'll need those in a second. Okay. Now, we're not going to copy this part right here, this part right here that I have here. This is just a bit of a background. But originally, right, organic meant natural, just coming from living things only, okay? And people thought back in the days, right, that the compounds that you have only came from living things, and that's it. But in 1828, scientist Wohler, okay, he synthesized urea. Now, what does urea sound like? Urea sounds a bit like urine, yes, and it's a compound actually found in urine. So he was able to do that in the lab. So organic does not have that definition anymore. But we will copy this definition here, folks, okay? That organic compounds are those which contain carbon, okay? So we're going to take that down right there. Organic compounds are those which contain carbon, all right? And organic chemistry is a study of carbon-containing compounds, okay? So this is a very important definition right here, okay? Moving on. Now, carbon on your reference table, right? You'll see it's the big C in the box right there. It has a number of properties to it. Now, I'm not going to fill in every last one. We know the symbol is C, right? And we want to look at the valence electrons, though. How many valence electrons does carbon have? Okay, it has 4 valence electrons. That's very important because in chemistry 1, if you have 4 valence electrons, right, what number are you trying to get to? You're trying to form a stable what? You're trying to form a stable octet, right? Yes. So you will form 4 bonds because 4 plus 4 is 8, right? So you remember that from Chem 1. So you can review your Chem 1 notes for that. No problem. So move on. Now, we're going to take these properties down, people. But this is a bit of a long video today, but we'll take these properties down. Properties for organic compounds. They tend to be nonpolar. Now, are all of them nonpolar? No way. But a lot of them, because they tend to have a lot of carbons in them, most of them, okay, a lot of them, okay, they tend to be nonpolar, all right? Okay, so they tend to have very low to no solubility, okay, in polar substances. Now, remember we did the topic of like dissolves like, so polar things dissolve in other polar things, and non-polar things dissolve in other non-polar things. Okay, so let's review that also. Okay, point number 2. Non-polar organic compounds are held together by that weak intermolecular force. What's that weak intermolecular force that holds non-polar things again? We remember it to be what? VDW, right? Van der Waals force. And sometimes the book calls it London dispersion, right? So look that up. Van der Waals or London dispersion. Okay, are there? That's why they're held together if they're non-polar. Okay, let's move on. For number, let me see what I did here. Let me go back for a second. Look at that. So for number 3, we'll change this number right here to 3, guys. Okay, for number 3, all right, organic compounds tend to have high or low vapor pressure. Now I'm asking you the question. If your attraction is weak, right, what's going to happen to your vapor pressure? Will it be easily to go into gas phase, or it's harder for you? Actually, your vapor pressure would be high if you have weak attraction, right? Because you release particles very easily because the particles are not strongly held together. Alrighty, no problem. This next point right here, okay, most solid organic compounds, right, tend to be soft, quote unquote, okay, as in fats and waxes. So the wax in candles and most animal fats and so on, the fats in our bodies, for example, are all organic compounds, okay? They tend to be non-electrolytes, okay, for the most part. Are they all non-electrolytes? No, they're not, but they tend to be non-electrolytes because they tend to have neutral molecules as opposed to having mobile charge. All right. So you can, once again, guys, pause the video as you need to take the notes, right? So I'm just going through these guys right here. They tend to be evaporate easily, okay, from solution. This is volatility, all right? It's volatile, all right, like gasoline, for example, okay? And these are properties, that you'll see of organic compounds. Okay, now let's look at this table right here, guys. We have CH4, right? We have C8 H18 and we have C24H50. Now notice, right, this CH4 methane, okay, natural gas, okay, it is in the gas phase, right? Natural gas, methane in the gas phase. Well, it's used in the Bunsen burners in the lab. It's also used to cook with, right? Okay, and this guy right here, C8H18, is actually octane, which is in the gas pumps. And this C24H50 is a fancy guy, which I'll show you in my next page. Okay, this is found in spices and so on. It's in the solid phase. So what if someone asked you, right, what's going to happen, right, as the number of carbons increase? What's happening in the strength of van der Waals attraction? If you're going from a gas to liquid to solid, is your intermolecular attraction, is it increasing or decreasing? Okay, your attraction, right? The attraction is actually increasing. Okay, and does that make sense that solid things have a stronger intermolecular attraction than things that are in the gas phase, right? Okay, good. So as you have more and more carbons, the larger the molecule, the intermolecular van der Waals attraction increases. Okay, so here we go. We have something called hydrocarbons, right? And from their name, they're made up of just carbon and hydrogen, right? Now, hydrocarbons, right? These guys that are just carbon and hydrogen are common families. Now, guys, I don't want you to panic because the thing is, right, if you look on table Q, okay, they have the families there for you. So you really and truly don't have to memorize them, okay? So there's something called alkanes, which we'll look at today. Alrighty? Okay. Now, I just want to take this down right here. This is important. Carbon, right, can form a wide variety of compounds, millions and millions of compounds. It could form compounds that are cyclic, meaning that they bond they're in a continuous bond all around, like this or like this right here. Or they can make straight chain compounds like this over here. Okay? Now, why is that? Because they tend to form what? 4 covalent bonds, right? Now, the thing is, you can get a wide variety of compounds from carbon. Now, there's 1, 2, 3, 4 right there, and so on. So carbon is very, very flexible in terms of forming bonds. So it's a very important point right there. All right. So, guys, here's the deal. This right here is table Q. It has alkanes, alkenes, and alkynes, right? I don't want you guys to stress these two right here today. We're going to look at alkanes today, all right? Now, what is alkanes? Alkanes are carbons, right, where there's only single bonds between them. This is a hydrocarbon, and there are only single bonds between the carbons. So what do I mean by single bonds? You have a C right here, you have a single bond, you have another C right there, you have a C right there, another single bond, and so on, okay? There's something called double and triple bonds, okay? So if you look carefully at the picture on your reference table, you see right there in the middle right there, between the carbons, that's a single bond. If you look carefully between those carbons right there, that's a double bond. And between these guys, that's a triple bond, okay? So be careful how you look at it. There's single, double, and triple bonds. We want to look at a single bonded guys today. Now, also look, folks, at table P. Alrighty, there's some prefixes there that you'll memorize in a second. You don't really have to memorize them because they're on table P. You use them as you need. But notice meth means 1. Okay, F means 2, and that's number of carbons, folks. So if I said to you prop, right, propane, right, I'm telling you that there's 3 carbons in propane. If someone says to you heptane, they're telling you there's 7 carbons, and so on. Okay, now how do we name and write simple alkanes? Now, guys, here's the deal. Remember, it's single bonds only, right, between the carbons, right? So if anytime you hear the suffix ane, it has only what? Only single bonds between the carbon. Now, here's what you do. You count the longest continuous number of carbons, right? And it's called the parent chain. All right. So if I do this, right, 1, 2, 3, 4, and I ask you, how do you name that guy right there? How do you think we're going to start naming it, right? You don't panic. You count 1, 2, 3, 4, right? 4 carbons, okay? And you go back to your table P right here, and you look on table P, and you see 4 carbons. Your prefix has to be what? It has to be but, right? B-U-T. So you write but down, B-U-T, right? And since there's only single bonds between the carbons, you add A-N-E at the end, and you get butane. That's your guy right there. Okay, so we use table P to help us. Okay, and so on. All right, so let's go to this page right here. Okay, this is our last page. Now, here's what I want you to do, guys. I'm going to do 2 examples. I want you guys to do the rest up to number 10, and I want you guys to take a picture and send it in to me. Okay, so let's do number of carbons. Let's do 1 carbon. Now, what's the prefix for 1 carbon, folks? The prefix for 1 carbon in terms of alkanes, 1 carbon will be meth. If you look on table P, right? Now, what do I put at the end if it's an alkane? I put the suffix A-N-E. That's methane. Now, what's the molecular formula? I only have 1 carbon, right? So I'm going to write C down, and it has to have 4 hydrogens around it. Now, I'm not writing the hydrogens in because for the sake of space, right? So each of these lines represents hydrogen for me right here, okay? So I got 4 hydrogens around it. Okay. Now, what is the structural formula going to be? It's going to look like this. I'll write the hydrogens in for this one. H, 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 right? And what's the condensed formula going to be? The condensed formula is a structural formula without the bonds, right? So you simply write CH4. C and 4 H's, that's the condensed formula. Let's do another one. Let's go to 2. Okay, now if I have 2 carbons, look at your reference tables, guys. What's my name going to be? My prefix will be what? Will be F, right? ETH, 2 carbons F. Now, what's my ending going to be? My suffix, since I only have single bonds only, ane. I'm an alkane, so my name is going to be ane, ending, F-ane. So I write 2 carbons down, right, for my molecular formulas. Okay. Okay, right this here. Now, this molecular formula ultimately is going to be CH4. This molecular formula is going to be C what? C2. Now, how many hydrogens am I going to get? Let's go back here for a second. We're going to use this formula right here, guys, to get our molecular formula. So if I have N is a number of carbons, right? So if I have 2 carbons, right? What's 2? See that right there? 2N plus 2. What's 2 times N? If my N is 2. 2 times N is 4, and plus 2 more, that'll give me 6, right? So I have C2H6 as my molecular formula. Okay? Alrighty. Okay, so this molecular formula is CH4. This molecular formula will be C2H6. Alrighty? How to write a structural formula? I write C, that's 2 carbons. Okay? And I write the hydrogens around it. Notice I have 1, 2, 3, 4, 5, 6 hydrogens around it, right? And my condensed formula, I take away, okay, the lines, and I'll get C, right? Okay. H3. How did I get that? C and 3 H's. Okay. And once again, another C. Write that down. And 3 H's again. Okay. Bam. All right. Let's do one more. I'll do a different color this time. Let's use black. All right, guys. Last one. So, number of carbons, 3. What's the prefix going to be for 3? Look in your reference tables. It will be prop. Let's go slowly with this one. Okay, or prop. All right. It's an alkane, right? Single bonds only between the carbons. So I'm going to say propane. Okay? All righty. We use that in the gas tanks to do barbecuing and so on, propane. Okay, what's the molecular formula going to be? So you don't panic. You go back here. You look at this formula, right? It's CnH2n plus 2. I have 3 carbons, so my N is 3. So what's 2 times 3, guys? 2 times 3 is 6, plus 2 more is 8. So my molecular formula is going to be what? It's going to be C3H8. Okay, structure formula. What do? I write 3 carbons down. 1, 2, 3, and I fill my hydrogens in. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so each of these lines right here on the outside represents hydrogens, right? Okay, and that's it. What's my condensed formula going to be? So this first guy right here, I take away the lines. I'm going to have CH3, okay? C and 3 H's, right? This second carbon, what do you think I'm going to write? How many H's are here? There's 1 there and 1 there, right? So I'm going to write CH2. And for this one, this last one right here, I'm going to write CH and 3. CH3 for my condensed formula. So all you're doing, folks, okay, for number 4, right, you would say what? You would say butane. You'll use the formula, okay, to get the molecular formula. You will have C4H10. You will write out your structure formula, and you'll take away the lines of hydrogens to get the condensed formula. So do that for me, guys. Send it in. Do it up to the last one, up to 10 decane. All right, guys. I know this video is a bit long. Hard work plus sacrifice equals success. I want you guys to please be safe. We will get through this. Take care.